My name is Josip Žubrinić. First of all, thank you very much for coming, and thank you very much for having me here. I'm a PhD student. I work in University of Zagreb in Croatia. My supervisor is Professor Velčić. Some of you may even know him. I think he was here 2 years ago. Had a seminar as well. And I'm going to talk about this joint work with Kirill Chernychenko. He works in University of Bath in England, and the topic would be related to homogenization of and dimension reduction in the theory of elasticity. So first of all, I'm going to give you the outline of the talk. So first, I'll give you some short introduction. We'll talk about this periodic homogenization and norm-resolvent asymptotics and estimates. And then I'm going to give some introduction into the theory of thin elastic structures. And we'll present you our results. And then, as much time as we have, we'll go in the methodology of the proofs. Okay. So first, let me just say what we mean by highly oscillatory heterogeneous media. So we know when we are dealing with some partial differential equations, we want to store the material coefficients in some object, tensor of some sort. And we would say that the material is heterogeneous if this function would depend on a space variable. And if it would depend in this way that it depends on some small parameter epsilon, and at the position x, it's equal to one fixed matrix at the point x over epsilon, and this fixed matrix function would be periodic in RD. We are dealing in the whole space setting here. Okay. We are dealing with in the whole space setting here, and if this matrix A would be periodic with period 1 in each direction, then this matrix A epsilon would be periodic with period epsilon in each direction, and this would define our material coefficients of highly oscillatory periodic media. And then we would assume, for example, that we have this uniform boundedness here, and this would make our problem of mild contrast, so no high contrast today. And then we can define elliptic operator in this way. It's a differential form. We have some domain of the operator. We assume that A is L infinity, so yeah, we have some domain of this operator. We might ask ourselves some natural questions, such as what would happen when this small period of oscillations would go to 0? And what would happen with the solution to the stationary equations, evolutionary equations? What would happen with the spectrum of A? And it turns out that a lot of these questions can be answered by looking at the resolvent problem for our operator A. And this picture here represents what I mean by oscillating periodic media. We see this cell, it's repeating, and the period of the cell is 4 epsilon. This is the illustration. And this is the resolvent problem for the operator A epsilon, and we will now give some known facts about this. So it turns out that you can define a fixed matrix, which you would call a matrix of homogenized coefficients, with this minimization formula on the top, where we are minimizing with respect to functions in this space, which is just space of periodic functions with period this y. We call y unit cell. This is the expression. And then you can, with this matrix, you can define another operator A0. Again, this elliptic operator with domain now H2. And you can look at the resolvent problem for this A0. And it turns out that you can immediately prove some sort of qualitative result, such as, for example, if the sequence of right-hand sides would converge weakly in L2, or 2 scale converge weakly, then you would have that sequence of solutions would converge 2 scale or weakly to U in H1. So you would have a link between this sequence of resolvent problems and this limit resolvent problem. But still, this doesn't answer our questions, such as at what rate do we have this convergence and what happens with the spectrum, and so on. So it turns out that these questions can be answered once you have this sort of estimates for the resolvent. This operator here is called, these are called resolvents, right? And if you have this sort of estimates, then you're good. And Birman and Suslina has done a great deal in this direction. So in their course of works from 2001 to 2006, they've given proofs for these 3 types of estimates. So first thing you can have is L2 to L2 operator norm estimate on the distance between these 2 resolvents. And it turns out that the distance of these two resolvents is of order epsilon. Then you can have L2 to H1 operator norm resolvent for this distance, but then you must include here one additional operator, which is standardly called standard corrector in the theory of homogenization. Again, you have estimate of order epsilon, and this operator might be small in L2 to L2 norm, but in L2 to H1 it's of order 1, so we cannot remove it from the estimate. And again, you can also obtain even higher order estimate in L2 to L2 of order epsilon squared, but you must then change this corrector operator a bit. And actually, today we are going to see this sort of estimates for the case of heterogeneous elastic rods. Professor Cherenichenko and Professor Velčić have already done something in this direction in the theory of heterogeneous plates. And we are going to do the case of rods today. Rod is, this is the rod, actually. And so I just want to make a comment on this thing here. So let's say that you were studying scaled resolvent where the operator is scaled with 1 over eta, and eta would be a small parameter. Let's say that you are studying this. You might be motivated for this from studying evolution equation, let's say, where this inertia term is scaled with this small parameter eta. And then you might look at this in this way. This eta is very small. This would be the same as studying not scaled inertia term, but in different time scale. And I'm talking about this because this is exactly what we will have in thin structures. This is exactly what's happening. We have these different scalings of inertia term. And for example, if this eta would be 0.01, then 10 seconds of this time t would be 1 second of this t tilde. So somehow in t tilde we would compress the events from this time t.
Excuse me,
yep.
It's studying A or A sub epsilon?
Here? Ah, yeah. Okay, we can put epsilon. Yeah.
Does it depend on time?
The operator, no. F. Yeah. It can depend on time. Yeah. So.
But it doesn't depend on eta, right?
On no. Yeah, I just wanted to make a comment that by multiplying the operator with some, by scaling the operator with some small parameter, you are somehow looking at events which are happening very fast, and you are trying to rescale the time to, you are looking at some motions, some waves, let's say, which are too fast to see unless you scale the time. Other people might say that you are actually scaling the density here in front of the inertia term. And for example, when Ani Raul was deriving models for thin plates in 1985, she said that you have to scale the density to see the limit model. Professor Tambacha also, when he was deriving thin rods, he said that he was scaling the density and not the time. So that's up to you. How do you want to see it? And let me give you now some introduction into this thin elastic rods. So elastic rod would be an object like this. We are dealing now with infinitely long rods. So first you would fix parameter h, which would be the thickness of the rod. And then you take some omega. Omega would be this cross section of the rod. You would denote by omega h. This contraction of omega, so small omega, such that we have this formula for the volumes. And then big omega h would be just a product of cross section and R. That's how you obtain infinitely long rod. We want to deal with heterogeneous rods, so we must again have unit cell. And this unit cell will be interval now because we only want oscillations in the coefficients to appear along the length of the rod. And you know, in theory of elasticity is actually a system of equations. So material coefficients are stored in the tensor of 3 by 3 by 3 by 3. And this tensor would depend only on x3 variable, so only on the variable in the direction of the length of the rod. We would take them to be L infinity. We want to have, this is some standard stuff for theory of elasticity. You have that this tensor is uniformly positive definite, but on symmetric matrices. That's because in linear elasticity you have the symmetrized gradients which appear. And these are some standard assumptions of the symmetries of the tensor, which would make your operator then symmetric. Yeah. And let me just say we want additionally to have this sort of symmetries. So you can define this central symmetry operator, which would take a point here and switch it back to its mirror image across the origin, and we want this omega to be centrally symmetric. And this would be the rod. This is my hand written picture, so I hope that you don't mind. This is some additional stuff which we need to get easier formulas. And this is what I mean by heterogeneous in one direction. So we see how this period of oscillations epsilon is appearing here. We have the thickness h over there. And I just want to make a comment that, so you see as we are going to do simultaneous homogenization and the dimension reduction. So dimension reduction as h goes to 0. And since we want to pose everything on some Hilbert spaces, we want to have fixed Hilbert spaces, we need to, it's a good idea to rescale this domain onto the domain of thickness 1, just to have fixed Hilbert space for every h. This would in return change our operator a bit. So I will show you in a second what happens when you rescale the domain. But the elasticity operator is given there. We have this tensor here which oscillates in the direction x3. We have symmetrized gradient of u. That's something standard for the linear theory of elasticity. The operator is given with this differential expression and its domain. And we are interested when both of these parameters go to 0 simultaneously. And we think that it's the most interesting case would be when they are of the same order. You might look at different regimes if you want. But for simplicity, we are going to say that epsilon is equal to h from now on, just to have simpler formulas. And this would be a resolvent problem, weak form of the resolvent problem for our operator A epsilon. And you see here we have rescaled these coordinates to be posed on the fixed domain for every epsilon. From now on, epsilon is equal to h, okay? And what happened is that you have now scaled the gradients here. So scaled gradient in first two columns from change of coordinates. So we now want to see what will happen with the sequence of resolvent problems like this when epsilon goes to 0. And again, easily you can prove some qualitative result, such as, for example, when epsilon will go to 0, then this sequence of solutions of these resolvent problems would converge to a function of this type, would approximate the function of this type. And in theory of plates, it's called Kirchhoff-Flav ansatz. I don't know if in the theory of rods we can also use the same expression. But let me just give you an idea what this function represents. So we see here we have B1 and B2, D and A. So 4 functions define this sort of function. B1 and B2 would be, so the solution to the problem of elasticity is a function which we call displacement. That's how much one point was displaced from its original position once we apply forces, right? And this B1 and B2 would be displacements in the out of line direction. A would be displacement of inline direction, so we might call B bending and we might call A stretching of the rod. And this D here would be the twisting of the rod, or twisting of the rod. And this function would satisfy in the limit. You would again be able to define homogenized tensor by some minimization formula or by solving the cell problem and then with corrector defining this operator. It would solve a resolvent problem like this. So what do we see here? We see that this is standard in the theory of dimensional reduction, that we have increased the order of the partial differential equation. This is now weak form of the differential equation of the fourth order in this B1 and B2. So that's what appears when you are doing dimensional reduction. So we have fourth order in B1 and B2, but we have second order in D and A. We also see that in the right-hand side appears this operator, which we call a force momentum operator. I'll show you what it is in a second. So actually what happens, so if you want to know the displacement of the rod, you don't need to know the whole information on the forces, you just need to know some of its momentums, and as we will see later on. And this is some interesting stuff. So let's say, for example, that you have some additional symmetries in this tensor of material coefficients. So these symmetries are stated there. We will not interpret them. And let's define these two sorts of spaces. L2, which we call bend, L2 bend, and L2 stretch. L2 bend, for example, would be all the functions in L2 on the rod, which in first two directions, so directions opposite to the length of the rod, would be even with respect to central symmetry, and the third component would be odd with respect to central symmetry. And let's say that we define stretch, L2 stretch, which where the first two components would be odd and U3 would be even with respect to central symmetry. Then you would have that under these assumptions, these two spaces would be invariant for our operator, which means, so you can prove this easily by plugging in the equations, which means that if you have forces which belong to this space, then the solution would also belong into this space, and the same thing with this. So these two are mutually orthogonal, and in the sum they give the whole L2. And this similar thing would happen for this homogenized tensor. So homogenized tensor on this Kirchhoff-Law, on these coefficients of Kirchhoff-Law function would split into two. You would have a bending part and you would have stretching part, but only in the case of these symmetries. Unless you have these symmetries, they are intertwined inseparably, and one causes the other, and you won't have this. So, and if you look back into this equation, then precisely that means that this part here would split into one tensor which acts only on the bending part, one operator acting on the bending part, and one operator acting on this stretching part. And you would actually have two equations which are not intertwined in any way, but only under those material symmetries. And we will actually use this assumption to get some sort of motivation for our proofs, but in the end we will prove stuff for the whole general situation. Okay. Here I can give you a picture of what I meant. So look, if for example you have a point here in the rod, and you have the force F2 acting in this direction, and opposite of that is the mirror image of that point, and if F2 in this point is the same as this one, if the same works for F1, but F3s are the opposite, then they would somehow cancel out, and you would expect this rod to bend out of line. But if you have opposite situations such that F3s are in the same direction, but F1 and F2 are opposite when you move to the central symmetry, then you would have the stretching of the rod and twisting as well. So this is just an illustration. And in order to give you the results, I have to define the operators. So I define the operator bend operator with this differential expression. I give you a stretching operator. There should be a minus here with this expression. And the whole operator, in case we don't have any assumptions on the material symmetries, would be given in that way. It would depend on epsilon. And this would be the momentums which I talked about. So you see, for example, F1 and F2 would cause the bending of the rod, but also the derivatives of F3 would cause the bending of the rod. And the whole momentum would be stored in this vector here. And now I can give you the results which we have. So the norm resolvent estimates would look like this. So we see several things here. I just want to make a comment on what do we see. So first of all, you see that we have scaled for some reason the operator with 1 over epsilon to the power of gamma. So for example, just look at this, these two and assume that we have these material symmetries. Then the most interesting case would be if gamma is equal, we can say that the most interesting case would perhaps be if gamma is equal to 0. Then you would, here this would disappear, here this would disappear, you would have the estimate epsilon on the right-hand side, and you would have much as what you expect. So this stretching situation is similar somehow to bulk case, to not having dimensional reduction. But in the bending case, for example, interesting case would be maybe if you would put gamma equal to 2. And if you put gamma equal to 2, then here this would disappear. But here you would have 1 over epsilon to the power of 2. And again, so in the theory of dimensional reduction, different components of the function would have different orders of estimate, unfortunately. But this means that precisely so, bending waves or bending phenomena would happen on different time scale than stretching phenomena. That's what you can see from here. So we see actually that the bending phenomena is much slower than stretching phenomena. So stretching waves would would oscillate very quickly, while bending waves would oscillate very slow. We also see that the limit resolvent is sandwiched here between momentum operators and their adjoints. We see also here this operator, which is a smoothing operator. I will show you in a second. Actually, this can be removed from the estimates, but it comes naturally with the proof. So keep in mind that it can be removed here. And
excuse me, can you show us again these homogenized operators, A-home stretch and A-home bend?
Yeah, sure. Here.
A-home stretch is of order 2.
Yes,
order.
yeah, and bend is of order 4.
A-home bend is of 4th order.
Yes, and in case you don't have these symmetries, then this operator is of mixed order. So you have some 4 derivatives, some. And their domain, so they act on the thin. The limit is the limit functions are posed on R only. So that somehow this sandwiching here translates some function on posed on R, then back on R3. And here we have some scaling. So in this bending case here, we are allowed to allow the forces in third direction to be a little bit bigger than the rest of forces. So somehow motivation for this might be that it takes a much higher force to stretch the rod than to bend it. So
what is P alpha
This is a projection on the first component and second component. Yeah. So this, or a third component. So we see that the first two components would have different estimate than the third component. And again, we have even L2 to H1 estimate, where you must include these operators, which I will show you later. These are standard operators in the theory homogenization. You obtain, so again, if you would put gamma equal to 0 here, then you would have here estimate of order epsilon, and something else in bending case and in the general setting. And also you have the estimates of a higher order L2 to L2, where you must subtract more. You must subtract another corrector, which is somehow strange. So I'll show you in later what's going on here. And again, if you would plug gamma equal to 0 here, so the reason why we scale with 1 over epsilon to power gamma is because there is no natural scaling here. You might want to see all of them, to see. So now we will go into the methodology of proofs. So let me see what time it is. Okay, so the strategy is somehow like this. We'll take Gelfand transform and transform this resolvent problem into a family of, into a continuous family of resolvent problems posed on a cell. And that would make the resolvent, then we would have a discrete spectrum, and it would be easier to analyze stuff. Then we would provide some a priori estimates of Korn type, because we're dealing with elasticity. And then we would perform this asymptotic procedure for calculating these resolvents. So much, if I have time, I would like to go through this procedure to show you. And at the end, we would combine these estimates which we have got into one single estimate by this contour integration, which I will show you at the end. So first, let me just say what we are dealing here. So this Gelfand transform, it's integral transform which takes a function in whole space, L2 of whole space, and would transform it in the periodic function on the unit cell, which is also, the additional variable here appears, which we call quasi-momentum, and it belongs to this cube here from minus pi to pi to the power n when there is the dimension. And it can be inverted, so you can calculate your function f with this formula here.
Excuse me, the letter n in the second formula is n is the index of summation, and n is.
Yeah. You are right. Yeah. Let's call this d as a dimension. Okay. Yeah. You're right. So we might look at this as we have decomposed the L2 into a direct integral of these L2 periodics, which depend on which are indexed with chi. But actually, we want to use some other version of this Gelfand transform, which is somehow more appropriate for our problem. So we are dealing with dimension reduction in and the oscillations are only happening in third direction. So we want this Gelfand transform to work only in third direction. So we will leave these two variables alone and only apply this to a third variable. And we have the oscillations with period epsilon. So that's why we have epsilon here. And this constant here is just to make this operator unitary. And it can be also inverted with this formula here. And this is what we are going to apply to our resolvent problem. And you see it commutes with the derivative, with first two derivatives, of course. But when you apply to a third derivative, you obtain 1 over epsilon here, dy of Gelfand transform of u plus a multiplication by this variable quasi-momentum I chi times the Gelfand transform of u. And this will be very important now, since Oh yeah, somebody might want to work on with Gelfand transform, which depends on this scaled quasi-momentum. Other people might want to work with the Fourier transform. It's all pretty much similar. So I can give you now the definition of that smoothing operator, which I promised. So it appears in the limit problem. So basically, this operator is you take f, you apply Gelfand transform to it, then you take the mean over the unit cell, and then you go back with Gelfand transform to the domain. And if you do some calculations, then it turns out that this operator acts like this inverse Fourier transform. So like this convolution of this function and f, where this means Fourier transform of f. And we see here that it's actually a smoothing. It cuts the high frequencies higher than 1 over 2 epsilon of f. And back to what I was saying. So we will take our form associated with a epsilon, and this scale Gelfand transform will have this property here, that our form for every u and v can be decomposed in this way. And the reason why we get this 1 over epsilon here is that so we already had this scaled gradients which had 1 over epsilon in the first 2 columns. But then when we apply this Gelfand transform, you also get 1 over epsilon in the second column, plus you have some dx3 plus I chi. So you would also have this 1 over epsilons in the third column, and you would have it twice, so you would have 1 over epsilon squared in front. 2 of them comes from dimensional reduction, and 1 comes from homogenization. And this form A chi is given with this formula here. So you have symmetrized gradient. First two variables are in omega. Third variable is in y. And then you have this operator I x chi, which is basically multiplication but I chi but symmetrized. So this is what you get by symmetrizing this part in the third column. And this would be our transformed resolvent problem. So it's now posed on omega times y. So this is a compact domain. So this is the weak form. We seek u such that this works for every v in this H1 periodic, which can be equivalently rewritten. If you would be using a Fourier transform, then you wouldn't have this operator I chi, but you would have different space. So whichever you like best, you can apply. And as an illustration, this is what happened with the resolvent. It's actually decomposed into a continuous family of resolvents, but scaled with epsilon squared. And now I can give you some strategy. So first we want to have some a priori estimates for the solution of this type of problem. And you know, in theory of elasticity, so you have this symmetrized gradient. And the symmetrized gradient in its kernel has functions which we call rigid motions. So rigid motions are functions of this type, ax plus c, where a is a skew matrix and c is simply a vector. And this means that those motions are composed of rotations and translations. And the standard Korn type inequality states that from u you can always subtract a rigid motion such that this difference is controlled by the L2 norm of symmetrized gradient. And if we can prove that we have the same thing here, but if you have u in this H1 chi, so this is a space of quasi-periodic functions. I forgot to say that. So h1 chi, we have u is inside if u is e to I chi y some w, where w is periodic. So if you are on this space, then you also have this sort of inequalities for coefficients of these rigid motions. And so now we don't see why we need that, but from here we can easily see what would be the form of the limit of the leading order term in the development of u, maybe. We would see that, so this is another lemma, let's say, that u can be approximated by u tilde, where this approximation is bounded by L2 norm of symmetrized gradient, where u tilde is given with this form. So we see that it already resembles that Kirchhoff-Love type of function which we saw earlier. We already have this d here and C3, which would be the stretching part, let's say, and this would be the bending part here. This I chi would become at some point a derivative with respect to x3. Where those coefficients appearing there are actually of the different orders. So these two coefficients C1 and C2 are bounded with 1 over chi squared symmetrized gradient, and C3 and D are bounded with 1 over chi. And now we want to derive some bounds on the eigenvalues. So we know that this operator now is on a compact domain, so it has discrete spectrum, and we can derive some bounds on the eigenvalues of this operator, which we obtain from applying Gelfand transform to our original one. And for that we can use Rayleigh quotients. So we have this minimax formula for eigenvalues with respect to Rayleigh quotients. And you know that when you plug these functions, when you want to calculate Rayleigh quotients of these functions, you would obtain that here you would have of order chi to the power 4, here you would have order of chi to the power of 2. And actually, so from this you draw the conclusion. So you have a presence of two-dimensional subspace of eigenspaces where the eigenvalues are of order chi to the power 4. You have a presence of two eigenvalues of power chi to the power 2, and the rest are of order 1. And in the case that you have additional symmetries, those where we talked before, where these two spaces L2 and L2 bend and L2 stretch are invariant for I, then this spectrum of A chi would decompose into a disjoint union of spectra on L2 bend and L2 stretch. And L2 stretch would have this simpler structure of only two eigenvalues of order 2 and the rest of order 1. And this spectrum on L2 bend would have two eigenvalues of order chi to the power 4 and the rest of order 1. So in the general case, you have this four-dimensional subspace of different order eigenvalues. Under additional symmetries, it would split into one part with power 4 and the rest of order 1, and the other part. And so this gives us the motivation for the asymptotics of the operator A chi.
Can you show us again this operator?
A chi.
Depending on the quasi-momentum.
I think I have.
Why?
So this is the operator associated with this form here.
Where do these eigenvalues of order chi to the power 4 come from?
They come from this bending part. From how do you mean where they come from? So you have that. So you have that you have two-dimensional space here, spanned with this constant C1 and C2. So you have two-dimensional space here, where when you plug this into Rayleigh quotient, you see that it's of order chi to the power 4. because of the bounds and this Korn type inequality. This is all the consequence of Korn's inequality, yeah, because it explodes when you. Yeah. So.
Finally, it is because you have thin rod.
Yeah. It's because of the yeah. This has nothing to do with homogenization. This is just artifact of dimension reduction. Yes. And so, if you would, so the strategy is like this. Instead of looking at this resolvent here, which we obtain when we apply Gelfand transform, we will instead study those two types of resolvents, where A is scaled with quasi-momentum, because we know that those are the subspaces. Those will provide us with bounds on asymptotics on subspaces which we need. But if you have additional symmetries, then you would have two orthogonal resolvent problems, one pertaining to bending part, the other pertaining to stretching part, and you can scale this one with chi squared and this one with chi to the power 4. And so now what we want to do is provide the asymptotics for those operators, but with respect to the quasi-momentum chi. And this would be the strategy. We want to calculate the asymptotics for those operators with respect to quasi-momentum chi. And then by some contour integration at the end, we will go back from this type of scaled operators back to this. But the structure of our work is like this. So first we do it for this problem and this problem just to get motivation for doing just to see all the stuff that's going on with these problems. And then we attack the general case where these two are intertwined, and I'll give you now what's going on. So let me see what time it is. So I wanted to show you this resolvent asymptotics, the way we do it, but it's really difficult to follow because it has different functions in this elasticity. So first two terms are of different order than the second term, and it's all really hard to write and read. So I'll just show you in the scalar case what we want to do, just because it's simpler to follow, and you can trust that we apply something like this to the elasticity part. So let's say that you now look at a resolvent of this type. And our intention is to seek seek U and to expand it into a series of terms. Let's say that we just expand it in this way: U0 plus U1 plus U2 plus U3 plus U error. We don't know so far what order are these. What would be the order of this one? We just have in mind what we want to obtain, and we would like to have that U0 is of order 1. So this is just the way of thinking, that U1 is of order chi, that U2 is of order chi to the power 2, and so on. And we would like to have this sort of estimates for the remainder, where they depend only on some constant, which depends only on the domain, on chi to the power k, let's say, and on the norm of the right-hand side. And let's say that we want to do this. And we take this ansatz and plug it into the equation, and we separate all the parts, and we obtain a lot of terms here, which are difficult to follow. And instead of looking at this, I have colored the terms which we think would be of the same order if we would have this scalings which we want. So if we would want U0 to be of order 1 in H1 norm, then this is the only term that would be of order 1. Then red are the terms which would be of order chi if we would have that U1 is also of order chi. And then we have orange terms would be of order chi squared, where this is also the orange term and this is also the orange term. We have violet terms here, this is also violet, and so on. And now I'm going to form a sequence of boundary value problems where I've taken only blue ones, where I've taken only red ones and orange ones, and so on. And I end up with something like this. So the only blue one was the first one, and I obtained the equation for u0, which basically tells me that u0 is a constant. I don't know how it depends on f. I don't know which constant it is. I just know that it's constant so far. Then I take all the red ones, and I obtain this boundary value problem for u1, which is uniquely solvable only under this condition that the mean of u1 is equal to 0, since we are looking for a periodic function. Then I take only the orange ones, and I obtain this problem for u2, but there is no need for this to be solvable. So I know that this is uniquely solvable under this constraint, and here also I must seek u2 to be of 0 mean, but there is no need for this to be solvable. But luckily I have additional degree of freedom in choosing this u0, this u0 here. I still haven't decided what u0 is. And by forcing the solvability condition of this, so why is this not solvable? So in order for this to be solvable, the right-hand side must be orthogonal to the kernel to constants. And then I force this to be orthogonal to constants. And I obtain this thing, this equation over there, which is tested against constants. Yeah, we zeros are constants. Immediately this term is 0. I can rewrite it in this form, and I see that this is actually the resolvent problem for u0, where this tensor, or which is number here, is defined in this way. So this is standard definition with cell formula with this corrector term u1 here. So I derived the equation for u0 from the solvability condition for corrector term u2. And then I would like to continue and go on to u3. And u3 would come from the violet terms, but there is no need to have a solution for u3. I have spent all my degrees of freedom. I have no way of, by posing the equations with only violet terms, I have no way of saying that it's solvable. So I must stop here and see what happens. So this remainder u error would now have would now satisfy this sort of equation. I would have this sesquilinear form on this side, which is this a chi. I would have some residual part here, which is composed of all the terms which I didn't eliminate. It would be in h-1 norm. It's easy to see of order c chi to the power 3. When you plug this here, you get c chi. And this is not enough for us to have this higher order norm resolvent estimates. So we want to somehow continue. And the idea is to do this thing, to again start from the beginning by introducing, so we have calculated these three. But we start from beginning by introducing this u0, u1, u2, which now we want to be, so this column is of order 1, this column is of order chi, this column is of order chi squared. We want u0 to be of order chi, u1 of order chi squared, u2 of order chi to the power 2, and so on. And again, we plug this in the equation, and these are the new terms which we obtain. And now we look, we have only one red term, we have 3 orange terms, and we have here 4 violet terms in this one, but we also have some violet terms from before, from these terms which we have not eliminated from this part. And okay, now it starts to look a bit messy, but first equation again gives me that u0 would be some constant. I have this boundary value problem for u1, and For U2, I have this whole mess of terms which I have just put together, which would be of the same order. And again, the idea is like this. So I want this to be solvable. For this, the right-hand side must be orthogonal to constants. For example, in the elasticity, I would want it to be orthogonal to rigid motions, right? So I want this to be orthogonal to constants. And again, I pose this solvability condition. And I see that it, in the end, turns up to give me this equation for U0, 1. So again, the solvability condition gives me the equation for U0, 1 by some expression on the right-hand side, which I'm not sure so far how to interpret. But this gives us some like diagonal procedures. So we in each cycle we come up with new 3 correctors, and so basically, and we can always prove the estimate on the remainder by using this Korn type inequality, and we have that this resolvent is expanded. So the first term is this is just constant here. And then we have this sequence of corrector terms which we defined. And now I want to go back to elasticity to show you what happens. So in the stretching case, we did basically exactly what I just described. We obtained that in L2 to H1 norm, you have this sort of norm resolvent estimate. You have this operator scaled with chi squared. This is the leading order resolvent. The difference is of order C chi. But then, so you have that U0, then you have U1, then you have U01. So then you must take these 2 terms if you want to have the estimate of the higher order. And this is exactly these 2 operators. First one calculates U1, and this is the standard corrector term. And the other one calculates U01, and this is a non-standard term. But you must subtract it in order to have this type of estimate. In the bending case, it's a bit more complicated. You have different estimates depending on the variable, and it's a bit more complicated. But you can also do this. So this would be under these additional assumptions. And you can also do this without these additional assumptions. It doesn't matter. You would just have 2 procedures for the same operator. So 2 sequences at once for this operator. Once you scale it with chi to the power 2, the other time you scale it with chi to the power 4. So you have this. And now I can just showcase how we come to the final resolvent equation. So this is the thing which we have for L2 to, we have L2 to H1, but let's say we just want L2 to L2. We have that this is bounded for sure with C to the power chi. But we want to go back to the operator which is scaled by 1 over epsilon to the power 2 was there, but let's do it for the 1 over epsilon gamma plus 2 for gamma greater than minus 2. And what do? You define a function of this type, which when you would apply it to this operator, it would just give you the resolvent which you need. And you know that, this operator A chi, these two eigenvalues which are of order chi to the power 2, for example. When you rescale the operator, you can, by using this a priori estimates, you can find the precise interval where they are for every chi. And this interval is in the positive part of the real axis. And that is a fixed interval uniformly in chi. And you have this formula here of Cauchy type. You can take a contour gamma, which would surround these 2 eigenvalues, both of the operator C stretch and both of the of the matrix C stretch and both of the operator A chi. And you would have this formula. This function applied to A times projectors onto the eigenspace, which is spanned by the eigenvalues surrounded by this contour, is given by this this expression where you have this here, the resolvent of the operator. And I just wanted to say that, so what did I want to say? So if you, let's say, have a bound on resolvent of type Z in the spectral variable Z of A minus resolvent in Z some operator B, and let's say that you want to calculate resolvent in some other spectral parameter. Sorry if I'm writing this messily. If you want to calculate this from this, you can do this, but you must multiply here with some coefficient of type maximum of 1, then Z minus W, distance of W to the spectrum of A. And again, the same thing with spectrum of B multiplied with this. So if Z is equal to W, then those are the same. If W approaches the spectrum of A, then this would explode, this constant here. So I'm saying this because this would precisely appear under the integral, and we don't need, we only need that this Z is uniformly far away from the spectrum of A, and this is precisely what we can do. We can choose these contours such that it's uniformly far away from these several eigenvalues, and once you plug it in, and again, you only need to provide estimates for this projected operator, because the rest is already of order 1 over epsilon to gamma plus 2. Only these small eigenvalues matter. And then when you subtract these two and go with the norm under the integral, then you provide the estimates for this resolvent which you have obtained by the asymptotic procedure. And you have that this function is bounded on the right half plane, and then that's how you come up with this bound. So for you end up with this expression here, and you choose the biggest possible, the worst possible case, which is when chi to the power 2 is of order epsilon to gamma plus 2, and that's how you end up with this. And just by using inverse Gelfand transform, you would come back to the original situation. And the interesting case is, so we are at the end now, is when you don't have these additional assumptions, then you have this operator, and you must provide the asymptotics for those two subspaces, and this method can do this as well. It's just you have the asymptotics for this one and for this one, and you just need to subtract what you get from both of them. And this is how you would calculate these normal zone estimates when you have different orders of eigenvalues. Yeah, and I have come to the end of the talk. Yeah, thank you very much.